All right, so we're just going to finish up these last slides that I wasn't able to get to in class today about heat. And so, as I mentioned in class, as we've been talking about, when we send more blood to the skin, that means there's going to be less blood available for the core. And so this means that surface blood flow, that blood flow to the skin, is increased at the expense of other tissues. Okay, so that's really going to lead to a decrease in blood volume in the core, which leads to lower end diastolic volume, lower venous return, which is going to decrease stroke volume, which is going to require you to have a higher heart rate to keep the same cardiac output. And that's why we saw in that previous slide that we have higher heart rate during exercise in the heat. And this is really what leads to cardiovascular drift. We also will lose some blood volume with sweating, but most of it is caused by that increase in surface blood flow. As mentioned in the previous slide, we also have a little bit of an increase in VO2 because we become a little bit less efficient. We use more glycogen because we're using the glycolytic system more, and the use of glycogen is tightly linked to how much fatigue we have. Okay, and so the sweating mechanism, as I said, is very powerful in the body. Humans have somewhere between 2 to 5 million of the eccrine sweat glands, which are the main sweat glands that do the work of cooling us down. Sweat's 99% water. As I've been saying, sweat's very powerful, and so if we exercise without sweating, we increase our temperature by about 0.2 degrees Celsius per minute, leading to thermal injury, which could include brain damage within 15 to 20 minutes of exercise. And so, as I said, without sweating, we don't really have the ability to do much exercise. And so, interestingly enough, the sweat comes from the blood, as we've been talking about. It's pulling plasma out of the blood into the interstitial space around the sweat gland, and then that plasma goes into the sweat gland in the coiled portion. And as the sweat goes from the coiled portion up to the surface through this pore, we reabsorb sodium and chloride, and so the sweat becomes a little bit more dilute as it goes up to the surface of the skin. And unacclimatized people can sweat about 1.5 liters per hour. Once you're adapted to the heat, some people can sweat up to as much as 4 liters per hour. And so 4 liters per hour, that's a lot of sweat, as you can imagine. 2-liter bottles per hour, that's a lot. And so I had this slide here not because I want you to know how to do this calculation at all. I have this slide here because I want to just show you the power of sweating and getting rid of energy. And so this is a believable example of a 154-pound person. They sweat about 2 liters per hour in a hot, humid environment. And we'll say about only half of that actually evaporates. The other half just falls off, drips off. Okay. If they exercise for 2.5 hours, okay, then this is going to create about 1,000 watts of heat. Okay, it's a lot of heat that they have to deal with, that 1,000 watts. But each liter of sweat that is dissipated, or that's evaporated, results in about 680 watts of heat dissipation, which is quite a bit. And so if we take that 680 times 2.5 hours, because we're only assuming that 1 liter per hour gets evaporated, that leaves us with 1,700 watts of dissipated heat. So that's more than we produced, but that's not included by environmental heat. So we've more than been able to deal with the amount of heat produced by the body, but that's not including how much the environment is heating up the body as well. And so in order to maintain core temperature in this case, we've lost about 5 liters of water in those 2 hours. We only have about 6 liters of total blood, but obviously there's more fluid in the interstitial space. But again, 1 liter of water weighs about 2.2 pounds or 1 kilogram. And so that means this person lost 11 pounds of weight in the 2.5 hours of exercise, which is 7% of body weight. So it's a lot of sweating in that 2.5 hours. Gets rid of a lot of heat, but there's a major effect on the body, especially if no fluid is replaced. Okay, and this little table just shows you kind of what we expect with the percentage of body weight lost as sweat and what we're going to see. So starting with just 2%, we have impaired performance, but then going down from there, if we're at 7%, like in that example on the previous slide, we're expecting major CNS disturbance, hallucinations. If we get down to 10% of body weight lost with sweating, then we're expecting heat stroke. circulatory collapse and death if not treated. Okay, and so again, when we have this water loss because of sweating, but also because of shunting blood to the skin, stroke volume goes down, heart rate has to go up in order to maintain cardiac output. And this is really the definition of cardiovascular drift. And this shows the importance of fluid replacement. A study that did exercise for 6 hours in subjects, which is just ridiculous. I don't know who would sign up for this study, but they did. And they show that this is heart rate here, showing the heart rate when you replace with water or saline, heart rate pretty much stays flat. With no fluid replacement, they're not able to exercise for the whole 6 hours, only 5, which is still a lot, and the heart rate is just going up continuously until they fatigue. And as we dehydrate, we lose physical performance. That one's pretty obvious. And the more dehydrated we are, the lower our performance gets.